All right, guys. My name is Farhad Ghayour, as I mentioned. Today's topic is on hardware-accelerated JavaScript with WEBGL. What I want us to kind of experience is the beauty at math, code, and design together. A lot of WEBGL talks tend to be quite technical, rightfully so. However, I want to kind of provide you with something a little bit beyond just the technicalities and have something that we can actually build together in this room and go home with, and we're actually something I'm proud of. So part of this workshop, number one, I really want us to have fun. That's the biggest factor. So if we're not having fun building a 3D application, we're doing something wrong, and more importantly, I'm probably doing something wrong. So just stand up and saying this is boring will change something. Number two, you have to be very open to failure and success. With graphics programming, it tends to be quite artistic. It's something that you just don't know right off the bat. You kind of tinker a lot with code until you get the desired effect that you're looking for. So that said, a little bit about me. First name is Farhad. My GitHub handle is github.com/FarhadG. And the best way to get a hold of me is my personal email address. It's, as you can see, me at, well, you can't see that, but firstnameg.com. I can share with you guys the slide decks a little bit later. I work for Digital McKinsey, based out of our San Francisco office. Prior to joining McKinsey, I was a core contributor to Famous's 3D rendering engine. That was basically, it's a rendering engine with a focus on having the DOM coordinate space and the WebGL coordinate space together in the same space as if they're living together. The next line, you can see this higher order functions. Me being at the end, I started out as actually a graphic designer. I love working with a lot of graphic arts. However, working with a lot of developers, I wanted to figure out how do I acquire the right type of skill set to bring a lot of these ideas to fruition. So naturally, I got into code, and I haven't looked back since. But I've always kind of wanted to kind of jump back into graphic design. So this is something that's really interesting about WebGL. It allows for you to kind of express yourself with a lot of these things that I was used to previously with a lot of graphical arts, but on the web. And what that means is that you have a lot of 3D artists, you have a lot of graphics programmers that are not used to web programming, and then you have web programmers, like many of us here, that are not used to 3D programming. So it's a really nice intersection. You can have a lot of these artists working in parallel with engineers, and for people like myself who are interested in both, you can actually learn both skill sets pretty easily. I'm also the maintainer of WebGL.com, as I mentioned. The site will be going up again by December. The focus is mostly on demos and building an online tutorial series and helping people learn a lot of the 3D math, high-performance JavaScript, and how that actually fits in with WebGL. So that's a little bit about me. The agenda of today's topic, again, as you can see, these slide decks are very ugly and simple because I wanted us to get out of these slide decks as soon as possible here. In the beginning, we'll cover a really quick overview of the raw WebGL API, some history, the rendering pipeline, and some examples. These examples range from drawing a basic primitive, like a triangle, to lighting examples, and to something a little bit more complex, which is interactions with a 3D object in a 3D scene. The example that I'll show, I think you'll find pretty interesting, is exactly the example that I implemented into a 3D rendering engine using a picking model, and we'll talk later about what that is. Later, we'll get into abstractions over WebGL, and what that means is just libraries that are built on top of this very complex API. So you have libraries like Babylon.js. Has anybody here heard of Babylon.js? Nice, that's awesome. All right, this is one that I generally opt in for. It's a little bit more modern. It's written with TypeScript. However, 3JS to this day seems to be synonymous with WebGL. Rightfully so. It's been around for many, many years. And it's the one that we'll be using for today's demo. Next one, it gets famous. You have many other frameworks out there as well. So we'll kind of dive quickly into 3JS and some of the features that it provides for us so we can kind of familiarize ourselves with the API before we get to the last part. It's our own exciting stuff. I want everybody in this room, if you have a computer, I would love for you to code along. We're going to be building a 3D application together. And obviously, for those of you over the web, I'll provide you the assets as well. And it's actually building a game. And it's not a very your typical game that you're used to. It's actually taking a game that's already built and converting it into a 3D scene. So I know you guys just got back from lunch. You're probably tired. I was going to save the demo towards the end, but I'll just show you to you in the beginning, kind of whet your appetite, and kind of hopefully have you alert for the rest of the demo. So what is it? The game is 2048. Have you guys played this game? Nice. All right, this is one of my favorite games. It's a very simple game. It's quite challenging, I guess, once you figure out the little quirks with it. The reason I decided to use this game, it's built with traditional web technologies, HTML and CSS. And I thought it's a really cool example to actually build this out into a WebGL scene, primarily because we can see where HTML and CSS fall short, even building it with a 3D application, which I'll show you later, that I actually built a version of it in HTML and CSS and kind of see where it does fall short. So why do we need WebGL? Do we need to introduce this type of complexity into a project? And I want you guys kind of, I think, realize the coolest part of this presentation is actually the name here. 2048 pushed onto 2048 cubed. And I think this is probably the coolest thing that I think I'm quite proud of. The reason for that is cubed. Again, we're going to be working with a lot of cubes here. It's built with Three.js, and it's three-dimensional. So if this presentation is absolute crap, I think that's the coolest part of this demo. So for those of you not familiar with 2048, let's quickly bring it up. Let's see here. I got the link down here, so I'm all ready to go. So here's the game. Simple. Again, you can download this on your mobile device. When you press left, all the tiles in this example, or these squares, they shift left. You press right, they all go right. You press up, they all go up. You press down, they all go down. And the point of this game is to actually merge cubes or tiles of the same value. So you can see that there are 2 and a 2 and an 8 and an 8. If I press left, they merge. Press down, 8. Press up, 4. I can play this all day long as I used to. Anyways, the goal of the game is to get 2048 and go way beyond this. So, again, this game was one of the top games in the App Store. I used to play it every single morning and before going to sleep. Kind of depressing, but it's the fact. Let's see here. So let's show you a version of this game in 3D using HTML and CSS. So let's go to 2048. Actually, not this one. CD HTML, serve. Let's see if hopefully this works. All right, cool. So this is the version of the same exact game with HTML and CSS, but they're using cubes. So again, you press left, right, down, right. Cool. So you can rotate this cube so you can understand what's going on here. Well, what's interesting, again, this is obviously using HTML and CSS, and you're starting to see a lot of z-indexing issue. That's why there's clipping here. And you can, obviously you can fix this. You kind of provide a little bit of distance between these cubes. But however, as cool as this is, it really falls short. Let me check this out. So let's add more cubes onto this. And obviously this is not the greatest strategy for playing this game. However, it seems to be doing quite well. Let's keep adding more. All right, you can see that it's falling short. Anyways, you can see the animations, right? It's not 60 frames per second anymore, right? Can you guys all agree there? Right? So it seems quite choppy, right? And again, this is using CSS 3D transforms. These transformations are actually GPU accelerated. If you're not familiar with that, CSS 3D translations like translation, skew, rotations, these are GPU accelerated. So I'm using a lot of the most cutting edge CSS techniques to even apply this, make this 3D scene in HTML and CSS. Yet it still falls short. So this is the reason why we do want to have something like WebGL. It is a bit of a complexity, and what's surprisingly, for Three.js is I actually wrote this with less code, and that's why I think it'd be really cool for this demo. There is a lot of hackery that I had to use to even get this HTML and CSS to work. With the WebGL version, it's quite simple. And let's see what the WebGL version of this looks like. By the way, any questions so far? How long did it take to get 2048? Oh man, I'll give you the honest answer. I was actually terrible at the game. My girlfriend at the time, she was amazing with the game, and she found a technique that beat me, and I didn't want to admit it, but I looked over her shoulder and I figured it out. So that amount of time to actually get 2048. But yeah, I realized if you decide to play the game, if you just keep going to one particular corner, you just kind of follow the snake model, as they say, you can get some crazy high scores. Yeah, I'll give you actually the repo for this. I don't want you to look at the code here yet because we're going to build it together. So yeah, good question, but it's not going to happen just yet because we're going to build it together. So All right, so let's get to WebGL. Okay, so this is the 3D version of this, not this one. What am I doing? 2048 cube, there you go. So this is the one that you're actually going to be cloning down. npm run start s. This is actually, we're using a lot of Webpack here for live reloading, and the reason I wanted to kind of provide you a boilerplate with Webpack and some other technologies in there is this game, I kind of want you to integrate with Angular or React or what other libraries that are out there, so you can have like a HUD display for your scores, just to kind of show you that WebGL plays really well with other technologies. So let's run this game really quickly. Actually, before, let me open up the text editor to kind of enhance the demo as we go along. Preferences. Let me see here. Editor, font. All right, let me go to a larger font. So, source. Not this one, sorry guys. All right, cool. I think we're getting somewhere. I have no idea what this one is about. Okay, cool. All right, can you guys see that code by any chance? Or is it too large? Because it's really large on my screen. All right, so we saw the traditional game. We saw it build with HTML, CSS, and 3D space. Here's the game in WebGL. It should load. All right, cool. Again, is this exciting or no? No, it's not, right? Again, you have to be honest here. It's not, right? But it's extremely smooth. And the underlying structure of this game is quite similar to the HTML one, yet I'm using WebGL to render this target into. I'm using WebGL as its rendering target, I should say. So what? Here's a parameter that I created. It's called true. So what's the point of this? Let's turn so what to true. Now you actually have a 3D representation of this. And this is very, I guess, kind of hideous. It's just like containers. You can understand the 4x4 grid here. So neat. Let's turn that on. Now we have depth with our cubes, right? Is it getting interesting for you so far? All right, cool. So as you mentioned, obviously in the HTML and CSS version, this was falling short completely already, right? Again, I can play this game, same effects. And again, I want to emphasize that it actually took less code and less overhead to even think about this game. Let's go to the wow factor. By the way, who's a fan of these parameters? This is my very intuitive API for building WebGL applications. So, wow. Now, we mapped it into a scene, right? And we'll be doing this together all day today. So it may seem like it's magic, but it's not. By the end of the day, you'll be creating this by yourself and building a lot cooler things on top of this. Now, WTF. Now, you can see that the cubes are reflecting the environment, and you have lighting based off of that sun. Can you guys see that? So now these cubes appear glass-like, right? At first, I actually made them chrome-like, but they were just awful looking. So I decided, and the colors are not the best choice of a color palette, but limited time, I guess. So anyways, you have lighting here, you have environment reflection models, and again, you have the grid helper helping you out. Should we go to Epic? Yes? All right, good. I was just going to stop there. So what's Epic? Epic, now it's 3x3, or 4x4, I should say, right? Again, super smooth, and you can see this thing. Real-time lighting effects. And you can get to something obviously much more complex. You can apply shadows here. You can apply a lot of physics simulations. But again, this is 2048. The game is quite simple, so we're not going to go that crazy with it. So again, super smooth, 60 frames per second. You can go crazy with this thing. And excuse me, I need to use the bathroom. So what is this? So as you saw, that the traditional game is based on a 4x4 grid. With WebGL, we can do a lot more primitives than that. So in this example, let's just actually increase the grid count. Right? So now this is on a 7x7 grid. You can do 10x10, you can do 50x50, right? The game kind of getting 2048 becomes pretty simple at that point. So to answer your question, David, it's much easier to go 2048 this way. So this is my hack around that job. So cool. So this is kind of the demo we'll be building together. There is still some bugs in there, and I've kind of let the code base where we leave off. There's going to be plenty for you to build. And by the end of this, we'll do kind of like a live Q&A about other implementations that we can build on top of this code base. So I really want you guys, at the end of this demo, to take this code base, add more functionality. Just head me on my email, and I'll help you if you have any problems with it. Or just send me your projects, fork this repo, and kind of inspire me with your creative artwork as well. So let's get on with some of the boring stuff until we get to the actual building of this application. All right, cool. So how about you guys? You know a little bit about me, what we're going to be talking about. How many of you heard of WebGL? Nice, okay. How many of you used it on personal projects? Okay, a few. And how many of you have used it in a production environment? Nice. Did you guys who use it in a personal or a production project, did you take the insane or the sane approach? Meaning, did you go for the raw WebGL, or did you opt in by using a library? 3JS? And somebody back there? I'm sorry? Got you. Cool. So good. That's generally the intuitive approach, right? You want to use a library, something that's a little more standardized with proper documentation. All right, and for you guys, you can kind of shout at once. I mean, not at once, but hopefully it's a little bit coherent. What do you want to know? You guys are all here with me. What's your intention being at this presentation with me? Any of you guys? What was that?
What is cool about the mechanic?
Cool.
How you structure your code?
Sure. And actually, I mean, we'll use a lot of the modern ES6 and ES7 features to build out this app. However, building a very complex game, you should really think about architecture. It's a very good question. I took a very simpler approach here just to kind of make the code quite concise, but we can talk about different ways of organizing your code. I mean, for one example here, I separated out the controllers, which allows for you to control the cubes. You have a manager that controls the entire game in general. You have an actuator. So you have an HTML actuator, which basically renders onto HTML. And again, I have a WebGL actuator, which renders the same scene onto WebGL. So kind of modularizing your code that way is very useful, especially for a project like this. Let's say today we actually achieve the things that we want to know. What do you guys want to do with this knowledge? Because when I first started WebGL, I was just like reading a lot of material, but it was just not useful. So I'm like, why do I want to use this? Does anybody have any projects that you want to work on? How do you guys want to actually apply this knowledge? Don't be shy. Cool. So I'm sorry, did you want to build a game with it? Is it going to be like a multiplayer game or? Cool. Well, even this game, like I'm not sure if it looks complex or not. It's very simple, and we'll get through with that. But you can turn this into a multiplayer game because obviously it's on the web. I was trying to think about how 2048 will be collaborative. I was thinking of ways that if you press left faster than the other person and merges cubes, you will get the point. But I'll leave that up to you guys. Cool. Anybody else want to share? Yeah, yeah, absolutely. I'm not sure. Yeah, so I'm sure you saw, but Unity recently raised a great deal of money, and that's I think primarily the reason WebVR and virtual reality has been really taking off, and there's a lot of funding going there. So, yeah, I think it's going to be a very interesting industry. And I think, I mean, with WebGL, it's something that I really encourage you guys to kind of dive into. It's a breadth of a skill set, but it's really cool because If you want to model your own objects, you would use something like Maya and Blender. And you would actually obviously need to know about web development and 3D programming. It's a very nice skill set to have, but allows for you to cover a large industry. And once you bring virtual reality into the mix, things get quite interesting. So,
Living and VR, what else can we, WebGL be used for? It's still not mainstream. So far, how far we have reached with WebGL?
that's a good question. We'll talk about it a little bit that later, but it's actually the standard. Look, I think what was it? Last year for us was great news. Apple for many years was not allowing WebGL to be enabled by default, but they enabled it on Safari, and more importantly, even on their mobile Safari browsers. But it's enabled by on all devices, all modern browsers. So I mean, in that sense, it is kind of the standard. WebGL, we're actually at WebGL 1.0. WebGL 2.0 has a lot of amazing features that are coming out, and it's going to make it even more performant. And I think with things like WebVR, it's really going to push the envelope, because you can imagine that a lot of these very interactive and immersive experiences on the web, they're going to require WebGL, so it's going to really push the envelope. And you have things like Vulkan, which is the new rendering API. It's much more advanced than OpenGL, and there's been talk that even the Vulkan API on the web will be called WebGL as well. So it's something.
Whether it is good at native platforms as well?
I'm sorry?
Besides web, whether it is performant on native platforms as well?
Yeah, that's a good question. So actually, we'll talk about that. So WebGL is a subset of OpenGL, and OpenGL is obviously meant for native application development, but WebGL is a subset of OpenGL, so a lot of the concepts flow through. So let's get to that. Thanks for asking that question. I am your father. So what does this mean? WebGL is a child. It grew out of OpenGL. If you're not familiar with OpenGL, it's a computer graphics rendering API. It allows for you to render high-quality images with basic primitives. It's the basis of many of the 3D applications on mobile and desktops. It's operating system and Windows system independent, which means that you can run your application everywhere with the correct build configurations. And like father or like son, the WebGL, it's an implementation of the OpenGL. It's the ES 2.0, which is the embedded systems for handheld devices and mobile devices, as you can imagine. It runs on all modern browsers, as you were mentioning. It's shader-based. We'll talk a little bit later about that. It computes using the local hardware. Again, it's GPU accelerated. It uses the HTML5 canvas as its render target, and it integrates really well with other web technologies. You can mix WebGL and React together, with any other technology you want to actually mix it with. Here's again is a simplified view of the pipeline. In the top, if you can see that, you have a set of vertices. A vertex is basically just defines a point in a 3D coordinate space. So it could be also 2D. You can have a 2D triangle, for example. But you basically have these vertices. Via a buffer, you basically load that into the geo context. Then in a vertex shader, you apply transformations to these vertices. Then those vertices are actually passed on, assembled, and rasterized. They're finally passed on to your fragment shader, and the fragment shader is responsible to determining the color of that specific fragment, in most cases, a pixel. And then finally, that's rendered onto your screen. Again, this is a very simplified view, but I think when I first started, it was really confusing to understand how the vertex shader and the fragment shader actually even interact with one another. To just kind of understand here, you have your vertices passed on to your vertex shader, and the vertex shader passes it on to your fragment shader later on. So understanding that flow is really useful, because you'll understand how these qualifiers that you have, such as attributes, uniforms, and variants in shader code, it becomes a little bit complex understanding that. So just visualize this and kind of remember this for our later talk. So in a nutshell, all WebGL programs, they must do the following. They create a canvas element. They obtain a drawing context. They initialize the viewport. They create buffers of data. They create shaders, and they finally draw. So we've been talking a lot about shaders. They're kind of scary. They're still scary to me. It's a constant learning process. Who here has heard of shaders? Cool. How many of you actually, I mean, they're enjoyable, but how many of you are actually kind of like deterred by it? Yeah, and I'll show you some examples later. It requires some complex math, a lot of in-depth knowledge, and it's something that I wouldn't recommend jumping off right from the get-go. So the approach that I took, and I want to kind of you guys maybe learn from my mistakes. I decided to go very specific first and then find myself back up and then go over breadth. I think with WebGL, it's much, much better to get breadth first and then go depth. I spent just tons of time just accumulating knowledge that I'm like, how am I going to use this thing? I couldn't build anything useful at all. So shaders is definitely one of those things. It's something that has an incredible amount of depth. So shaders, it's basically a function or a computer program that allows for you to manipulate vertices or fragments. You have two shaders, for example, in this context. A vertex shader, it's a shader that's executed for each vertex. So you can imagine that the vertex shader, you can apply some sort of transformations to a particular vertex. Some ones that could be, you would have translation transformations, rotation transformations, projection transformations, and whatnot. You can also do per vertex lighting. So if you want to calculate the lighting of a scene, we'll talk a little bit later about how important lighting is in a scene. But you can do computation of lights within the vertex shader, which is quite interesting because let's say you have a basic triangle has 3 vertices. You can compute that the angle of the light and be able to shade that given polygon from 3 vertices instead of per fragment, because that computation in the fragment shader is far more expensive. So you can do it per vertices and have the interpolation of the rasterizer and the triangle assembly take care of that for you. The fragment shader is obviously executed for each potential pixel, and I say potential pixel because a fragment does not directly relate to a particular pixel. Some scenes might have more fragments than pixels, and vice versa. There are a lot of effects that you can do in a fragment shader. This, again, we can do per fragment lighting. This is more realistic lighting examples. They're a lot more expensive. You do texture and bump mapping. As you saw in the cube example, we have mapped on, the numbers on the cube. Those are actually textures mapped onto that cube. Environment mapping, you also saw where the clouds actually were reflected onto the cube. So it feels like the cube is actually in that environment. Even though the vertex shader and the fragment shader seem required to even compile a program, you don't have to have the vertex shader with doing anything. Some very brave developers, they basically actually develop their entire scene in the fragment shader alone. And what that means is that you don't use vertices to even define objects. So just think about it really quickly in your mind. How would you define a cube, right? How would you draw a cube not even using vertices, right? Because we think about a cube as being some sort of given vertices, and then you apply the material over that cube. But how would you actually draw a cube without the vertices? And this is, it's quite complex, and people are actually developing entire scenes purely in a fragment shader. They're coloring each pixel based on some sort of functions. And a really, really cool website is called Shader Toy. Let me just show you this really quickly. These are a lot of examples that are purely fragment shader based. Let's see if this loads. Again, as I mentioned, computation in the fragment shader per fragment is a lot more expensive than doing it in a vertex shader, but it allows for you to get a lot more photorealistic rendering. Let's see if this works. It says in the tab that it's working. Great. Okay, cool. By the way, if I'm speaking a little too quickly, just raise your hand. I can slow down a little bit. All right, nice. I generally speak quickly, so I'm shocked to hear that. Or you guys not being honest. Yeah, so, the network is a bit slow, but you can see some of these complex scenes are purely done in a fragment shader. There are no vertices here at all. A really cool one here is a physically based rendering of water, and you'll see how realistic this looks, and it's absolutely mind-blowing. I won't load the other one because I think it's going to even take longer to get there. So definitely check out this website for inspiration. The code, it seems quite cryptic. These are the things that I was talking about getting breadth first and then going depth. So when I first started, I started looking at this stuff, I'm like, no way I'm ever going to start with WebGL. So having that breadth and kind of building cool things and then learning as you go along is a much better approach. It may seem intuitive to some of you guys. It wasn't to me, so I paid the lesson. Let's see here. See if this loads. come on, come on, come on, come on. All right, in the meantime, let's get on with this thing. So GLSL is the language that you use to write shader code. Even though the WEBGL is a JavaScript API for accessing OpenGL ES 2.0, the shader code is still written with GLSL. GLSL is an OpenGL shading language. It's C-like with C++ features. It's extremely efficient for matrix and vector arithmetic. Both Vertex and Fragment shaders are written in GLSL. Each shader has a void main function that it calls for determining the position or the color of a particular fragment. So just a quick overview of what GLSL is about and why that language is super useful for writing shader code. You have your scalar types. Again, it's a type language. You have floats, ints, and booleans. You have vector types, and you can think of vectors as like an array, right? So a vec2 is a two-dimensional array or two-dimensional vector. By default, these are float-based. If you want a vector, a two-dimensional vector of integers, it would be ivec. Of booleans, it would be bvec3, for example, for a three-dimensional vector. You have matrices, the 2x2 matrices, 3x3, and 4x4. Texture sampling in your style constructors. As you can see on the bottom, you define the variable with the given type that it needs to be. And on the right side, you're actually defining that three-dimensional vector. What's really cool, I wanted to add, even though the three-dimensional vector on the right side is set that is, you can actually compose different vectors together. So you can have a vec3, and within that vec3, you can have a two-dimensional vector, and then put the last component in. So the language lends itself really, really well for writing very concise code that's extremely powerful. You have your standard arithmetic operators from C and C++. However, they're overloaded for a lot of matrix and vector operations. So you can see you have a 4x4 matrix, which you can kind of think about as a 4x4 array. And you have a vector. Here is four-dimensional. Again, it's a four-dimensional array. And you're applying that vector, multiplying it by a matrix. And you can imagine in JavaScript, we would do some interesting for loops here to apply that, but it's built into the language, and it's super efficient because the GPU just gobbles the stuff up like nothing. And order matters, so the vector times the matrix is different than the matrix multiplied by the vector. You have components and sizzling. I think this is a really cool part of the language that JavaScript doesn't provide you, for example. So you have this array or this vector. If you want to access the data within this vector, you would generally just do index 1, index 2, 3, 4, starting at 0, actually. But you can also access it XYZ, RGBA, STRQ, and these are more semantic ways of accessing data. But the reason that's really useful is that you can actually, for example, do vec3 BR, for example, and that would actually reverse the order. You would actually get the B component of that vector and the R component of that vector. You can get information and set it that way. So you can imagine in one line of code, you can set and get information that would take you maybe 5 or 6 lines of code in JavaScript. And at the bottom, you can see that the component swizzling, a.xy equals b.yx, right? It's quite powerful. It's really nice. And if you'll see on a shader toy, there it is. Perfect. So you see that water, right? You may think it's a video, but that's purely done in the Fragment shader. That's real-time rendering. I can take this code and manipulate it. And I mean, this code is quite cryptic, but in 188 lines of code, you have something like this. Let me make this larger. It's amazing, right? So you can see that this is why GLSL is so powerful, because in a few lines of code and it being GPU accelerated, you can get some profound results here. Qualifiers, these are the parts that I mentioned, that how you actually set and gate data within your Vertex and Fragment shader. Your attributes, this is a part that really confused me, and I hope I can kind of clarify it for you guys. An attribute is per vertex. So it doesn't make sense to have an attribute in the Fragment shader. Can anybody explain why? If you want to take a stab at it? Yeah, I mean, this is something that was really confusing for me in the beginning. That's
Maybe because Fragment shader does for every pixel and cannot have so much data.
Okay, that's an interesting input, but the Fragment shader can have a lot of different inputs. But again, attributes are per vertex, right? So if you think about it again, what is the Fragment shader responsible for? It's for determining the color of each pixel, right? So the attribute per vertex kind of doesn't make sense because the vertex data sits inside of the vertex shader, right? So an attribute, for example, of a vertex could be the position of that vertex and a normal. And who here is familiar with that concept of a normal? Great. So a normal is actually quite simple. If you have a plane like this, my arm, the normal is the vector that's perpendicular to this plane. And why is that useful? Because it allows for you to figure out the orientation of this particular plane, right? So the normals of a vertex, the position of that vertex, these are attributes that are applied to that vertex. That's why these attributes only sit in the vertex shader. If you want to pass that data from the vertex shader to the fragment shader, the only way to do that is using varings. And you basically set varying of this variable type, you give it the data, and you can access that within your fragment shader. I know some people are yawning, some people are tired, you guys just ate a whole bunch of food. In the meantime, do you guys have any questions about this? Because this is like a really, was a confusing part for me. So, any questions? Cool.
The code that you showed in the previous slide, can you go back?
Sure.
You showed it in a different tab, I guess.
Oh, was it the shader toy example? Sure. What's your question? Until this thing, oh, actually nice. It might just load quicker than I expected. Oh, here's the other one.
So what language is this? GLSL?
This is GLSL, exactly. And that's a fragment shader right there.
And how does it reach GPU? This is browser. It understands only HTML using JavaScript.
Yeah, that's a great question. That's exactly what WebGL does, right? It's basically it allows for you to access the underlying hardware, the OpenGL standards, which is OpenGL ES, via the JavaScript console. So what you would basically do is write this shader code and create buffers. We'll kind of see that a little bit later. You create these buffers, and then you write this type of data input into the buffer, and you can access data within this fragment shader. I'm sorry? Is it transpiled? Yes. The GLSL code? No, the GLSL code is basically directly put into the GPU. I'm sorry? Yes, C or C++ like. It's just a subset of that. You don't get the entire language. It's basically a subset of what would be useful for writing shader code, basically a graphics code, because you don't need all the features of what C++ or C would actually provide you. But it's very C-like in nature. So we have 40, I'm actually already way over this. Some built-in variable, actually just really quickly, qualifiers and then uniforms are basically constant variables that you can apply within the vertex and fragment shaders. You have built-in functions like square root, power, absolute, trigonometric functions, and you can create your own functions as you would in any other language. Built-in variables, these are extremely important. Your vertex shader has these built-in variables, which is GL position. It's the one that's required, that it expects this is the final position of that vertex, for example. And in a fragment shader, it's GL frag color. So these are the variables that you'll see in every single vertex and fragment shader, because these are the variables that actually determine the final output of the vertex position and the final color of that fragment. You have other ones that are useful, geofrag core, which determines the fragment position as well. A really quick example of this in raw WebGL, let's go with this here. Okay, cool. And I'll quickly cover this. So we're drawing a basic triangle here, and this is like a classic example in WebGL. In the top, if you can see this, you have a traditional HTML element. This is obviously in a JavaScript context here right below it. We create a canvas element. We load up the vertices. It looks like a three-dimensional point, even though it's two-dimensional. And what this negative 5.50, what that means, you actually don't even need the last two. You got to change some data below it. But negative 5, the origin is dead on center. So this is 0, 0. Negative 5, 5 is the top here. The second two is negative 5, negative 5. So it's the bottom of this triangle. And 5, negative 5 is the bottom right of this triangle. Then you would create the buffer here. You would bind that buffer, you would write into that buffer, you would unbind that buffer so other data could be used. And a lot of boilerplate code. So here's an example of a very simple Vertex shader. We basically get the coordinates that we're setting within the JavaScript coordinates or JavaScript context. We set it directly. As you can see, as I mentioned, you have a 4-dimensional vector. Coordinates is a 3-dimensional vector, and you're applying the last component, 1.0. Below it, you have a fragment shader, basically just applies that as being red, RGBA, and you can see here R being 1. Yeah, great question. So this fragment shader or this vertex shader here, right? As you can mention, again, is an attribute, and we set this from the JavaScript context. Yeah, great question. And again, this GL position, you're wondering where did this come from, right? These are the built-in variables. Exactly. So a lot of boilerplate code, right? You keep going down, then you basically right here you can see here you're linking up the shaders to the program. You're getting the coordinates, right? And you're writing the coordinates. And at the end, you finally draw using the geo triangles drawing primitive. And there are different types of drawing primitives. You have triangle, strip, points, and they have different types of algorithms that they're optimized for. Again, this is a lot of code, right? For drawing a basic triangle. We can do this with such little code with HTML and CSS. That's why I think it's quite useful to use a library and later on dive down into the depths of what WebGL is about. Transformations. Do you guys have an idea what transformations are, really quickly? Yeah, exactly. So can anybody kind of quickly guess why a 4x4 matrix would be really useful as a transformation? Absolutely. So David mentioned that you can do a lot of 3D transformations in a 3D coordinate space with transformations. But what's really cool is, I like to add this in, is have you guys used with CSS 3D transforms, or even the skew or scaling, for example, right? You would take a div, you would scale it, right? And then you would rotate it. And every single time that you apply these transformations, it's a computational cost. A 4x4 matrix is your ability to compact a lot of different transformations into one 4x4 matrix and apply that at one time. And that's why in shader language, it's extremely powerful to be able to have all these transformations comprised within a 4x4 matrix and apply to that vertex or that particular fragment. So you can see here, for example, here's a projection set of matrices applied for getting a 3-dimensional scene rendered onto a two-dimensional scene. At the end of the day, your screen is 2 dimensions. So these are a set of transformations you'll be applying to that particular vertex. I'll go past that. Okay, lighting. Lighting is extremely important in 3D programming. And the reason for that is that when you first think of lighting, you're like, oh, whether this room is lit, right? But what's more important about lighting is that it determines the material composition of that object. For example, you can see that this carpet tends to be less or more shiny than this surface up here, right? So the way that the light interacts with that given object tells you the material composition of that. So lighting is extremely crucial for having a photorealistic scene, not just whether an object or a room is lit. It tells you about the material of the different objects, right? Again, lighting generally is done on a vertex shader because it's a lot more quicker, but you can do it in a fragment shader for much more smoother shading. Surface normals, these are used for calculating lights. So if you have, again, my plane here and a normal pointing upwards, and you have a light source from this angle, the light vector pointing and the angle difference between the light vector and the normal, you can determine the intensity of that light. Does that make sense? So at 45 degrees versus being exactly dead on, the intensity of light on that particular fragment is a lot more. But I want you guys to kind of understand something here. This is really, really cool. And I think if you kind of grasp the idea, if you're already not familiar with it, it should kind of blow your mind, I think. So you have a flat surface, right? And how you determine the light intensity of a fragment is based off of that normal, right? But who's to say that you cannot manipulate these normals, right? And get different types of texturing. So for example, I have a flat surface and I apply a texture onto it, like my skin, and my skin is not obviously perfectly smooth. I wish it was, but it's not, right? How do I get instead of manipulating a very complex set of geometries of mimicking how my arm actually looks, because that'll be a lot of vertices, right? What I do, I actually have a flat plane. I apply a texture over this plane, and then I actually apply transformations only to the normals. So this normal, instead of being pointed straight up, won't be pointing this way, won't be pointing this way, won't be pointing this way, even though the plane is perfectly flat. And when the light is being calculated to that against that normal, you can give the impression that that object is a lot more bumpy, for example, than it really is. Does that make sense, everybody? Right? It's a really cool technique, and this is what's used in bump mapping, normal mapping, to give the appearance that something has a different texture. WebGL lights example. Let's go here. This is on GitHub if you guys want to look at the code base for this really quickly, but I don't think this stuff is the interesting part of this demo. Texture mapping is basically, I think somebody here was talking about building a virtual assistant application in 3D Scene. So texture mapping, great. Texture mapping is the ability to map a texture or an image or even a video onto a 3D object. And how would you apply a 2D image onto a 3D object? It's kind of difficult, right? But if you think about a sphere, if you unwrap the sphere, right, and you would map the coordinates of that texture, for example, here you could see, and it's used S as the x-axis and T as the y-axis because you don't want it to be confusing with the traditional coordinate system. But the coordinate of this particular point on this texture is mapped onto to this particular coordinate in the 3D system, and you would basically apply some sort of algorithm, and there are different types of algorithms for this. You would map that texture onto that 3D object as if it actually is encapsulated over it. Interaction with ray casting, so there's different types. So in DOM, we take this for granted, right? You would query an element, you would say dot on click, do something, right? Very simple. It's a lot more complex in a 3D scene. In Canvas, when you would draw a 3D object, it has no idea what that object is really about, how you interact with it. So there are different models for having interaction built. One option is called interaction with ray casting. You would basically cast a ray into the scene, you would project it, apply all the necessary transformations, and follow that vector and say, hey, did it hit an object? Then I hit it. But what's really cool about this is that lighting, for example, in this room, you can see there are multiple light sources, right? But if there was only one light source, does that mean that the person in the back would be completely dark? No, right? Really quickly. In a natural world, right, that light bounces off many different objects. Right, so there's a sense of ambience or global illumination in this room. So interaction with ray casting, you can see this in a lot of movies. That's why like a rendering or frame in a movie may take many, many hours because they're applying many very complex lighting examples. What they're actually doing, they're casting this ray into the scene. They're following that vector as it bounces out around the scene. And the amount of times that it's bouncing around that scene, you can get a more photorealistic lighting simulation, right? But that's extremely expensive, as you can imagine, because if you have a very complex scene and you're shooting off rays into the scene, it gets quite expensive. Example here, there's another model called picking. This is actually one that I'm really fond of. It's extremely simple to implement, but it's quite genius. Quickly, everybody, raise your hand. Who here has played Duck Hunt, the game? Nice. Yeah, I used to play it as a game. It's a game I used to play in the Nintendo, I believe. You would basically shoot the screen, and you would determine whether you hit a duck, right? Who here can guess how that cheap plastic gun, right, pointing at a TV that has no idea what that gun is about, right? How would it know that you actually hit a duck? Can anybody guess? What is it? There's a cheap plastic gun, man. That's very complex. I wish they had that because that would be a cooler way to actually play that game. I'm sorry? The color? Okay, again, it's a very cheap sensor. So if you have this game, right, you have all these imagine a duck, it has a kind of gradients from dark green to light green, right? And amongst the trees, like, wow, that's crazy. That game was pretty cheap when I bought it, right? Unless they were not making any money. I'm pretty sure they made money on that game. So how did they make that? Dave, you ever had a guess?
I was going to guess the native duck completely red or green or blue for a split second and then capture the color of that pixel.
Dead on. So
I've done formats cooking in WEBGL.
Yep. I think this is absolutely genius. So quickly, to show you the game, and I think I'm going to ruin your childhood because if you've never seen this flash, it is there. It's kind of sad to say if your childhood was ruined by understanding this game, it's pretty bad. So, all right, let's see here. Once this loads, but yeah, essentially what the game was doing, the moment that you would click the trigger the gun, the entire scene would render black, right? Kind of like that. But it was actually loading in the game. It would render really quickly, flash black, and the hit targets, the ducks would be white, right? And your gun will determine whether is it pointing at a white pixel, which is very easy, or it's black. So you're on the right track, right? But it just needs to be a little bit more simple. So then you can imagine, so let's just see this flash so you guys can believe me here. You see that flash? Right? Again. You see that? It's very obvious when you look at it now, right? Sorry to burst your bubble. But what's cool is that I remember as a kid, you would be able to point at the wall, right? And then keep shooting, and then you're hitting ducks all over the place, right? One of the first iterations had that issue. But what they would do actually, it was they would render the scene, and they would have different types of colors for different types of ducks, and it would render it 2 times whether you actually hit the duck or not. So there's some clever ways to get around that. They fixed that, of course, right? But it's what's really interesting, I actually use the same exact approach in WebGL. And before casting a ray into the scene, which is quite expensive, I basically rendered the scene, applied colors to different geometries, and say, hey, did I actually hit an object before I even casted a ray into the object for complex lighting? Does that make sense? So it's a nice way to kind of prune the scene prior to even casting a ray onto the scene. But what's really cool, you can think about this, is that colors, but you have like millions of geometries in a scene. Do you really want to apply green, red, blue to all these different colors and manage that? And you're limited, right? So there are different ways of encoding that type of data into the Vertex Shader and Fragment Shader. You can actually do based off indices. And then, again, let me just show you the code really quick. I think you'll find this quite fascinating. So WebGL lights here. Again, this is quite a bit of code just to get this. You guys must be tired after all the food in combination with the boring presentation here. Hopefully we'll get better very soon. Okay, let's get this working here. Main.js. Hopefully this works. Come on. All right, right here, I'm actually doing the lighting within the fragment shader, so it's based per fragment. It's a little more expensive. And you'll see that this code is, I kind of commented it out for you guys so you can actually kind of follow through if you really want to build this out yourself. And sure. So in here in the fragment shader, you can see that I'm doing basically the dot product of the light direction and the normal. This is determining the difference in angle between those 2 vectors. And the diffuse is for the specularity, the glossiness of that object. Ambient, I'm providing just a simple global illumination into the scene. And again, it expects, at the end of the day, a frag color. It's a 4-dimensional vector adding the diffuse plus the ambient and the opacity being 1 here. Yeah, so I love your talk about Node.js debugging, right? Dude, yeah, debugging, like debugging in GL in general, it's a lot more difficult. Something that, you have a WebGL inspector, which is quite useful. You can kind of understand, hey, am I writing the right vertices to this given object? But in 3JS later on, we'll show you that I'll be falling down as we're building the game constantly because we'll be doing live coding, right? But there you can build helpers to kind of allow for you to say, hey, this is the general idea where my camera is. More often than not, your scene is good, but your camera is just pointing the wrong way, right? And understanding, hey, the orientation of your camera, the orientation of your scene. Yeah, these are things that's what I'm saying. You have to be really open to this experience of constantly falling down because it's just part of it. And it is frustrating, but once it's there, you're good to go. But within the JavaScript context, obviously you have your traditional debugging abilities. Within the shader language, you have tools like WebGL Inspector to kind of help you out with that. And here it is, a beautiful cube with per fragment lighting. It doesn't rotate or anything like that. So, WebGL picking, let's see what this looks like, and we'll go with the index encoding instead of the color encoding. This is the difference between putting indices into the shaders instead of color-based. Let's see when this loads really quickly. Again, the moment that you click on a canvas, I'm clicking off a uniform variable saying that, hey, I'm in picking model, then I render the entire scene. And in the fragment color, right, the GL frag, instead of writing the RGBA value being a color, I'm actually writing indices. So it'd be 0001. That's index 1 for a given geometry, right? So the WebGL context, the shaders are thinking that I'm writing a color, I'm actually writing indices, right? So I click, I render the entire scene really quickly, and I write all the indices, and I say, then again, I choose the color, I pick that color from the canvas, because you can do that, and say, hey, did I hit a value, an index? If I did, then I know it maps out to a geometry. So same exact model as a Duckhorn model. And you can kind of see that here. So if the pick face, if you're there, write the index over 255. And what's really cool about this, instead of, you can imagine, since it's 4-dimensional vector, you would have 255 for the first one, 255 for the second, 255 for the third, and 255 for the fourth. That's generally a little over than 1,000 objects. But what you could do, you can actually change these numbers to, instead of being base 10, you can change them to base 255, where you can have billions of numbers there, right? I would argue that having a scene with billions of objects you're interacting with is probably it's not the most intuitive scene, but it is possible. So you have a basic pyramid, I guess you could say, lighting here, and I click on this, and it actually colors it, right? And you don't see a flash because I don't need to actually render the scene onto the screen. I'm just rendering it into the GL context, grabbing the color, and you're good to go. You can also render the same exact scene to an off-screen frame buffer for different types of techniques, but you can also do this to make this a little bit more efficient. Does that make sense to guys so far? I think it's a really cool technique, and I kind of wanted to share that with you guys. All right, let's go to the next one. Okay, and even though it seems like graphics programming and with the capabilities of the GPU, it seems like it's the amazing thing, right? We still have to think about performance. These scenes are quite complex, and we have to take into performance and what we're rendering into the screen, or equally, not just what we're rendering into the screen, but what we're actually not rendering into the screen. So if there are scenes that are not in the object, or if you're only seeing the front of an object, do you really need to render the back of it? So these are optimizations that you can take. There are different ways of packing data into a buffer. For example, if you're loading millions of cubes into a scene, instead of constantly writing into buffers, you would pack all that data into a single buffer and write it one time into the scene. Another one is basically more efficient shaders. For example, I mentioned doing things in the Vertex shader instead of the Fragment shader. So performance is still an issue. You always have to think about it because you're drawing very complex scenes. All right. I'll use David Kerr's approach here. If you guys wanted to stand up really quickly, because we're going to get to the cool parts of this. So again, it says keep calm and sigh no more. I showed you a lot of code. It's a lot of raw WebGL code. It's things that generally when I saw in the beginning, I'm like, there's no way in hell I want to be jumping into writing WebGL code, right? That's not what I wanted to do in the beginning. So we're going to be using a library called 3JS, and get your computers ready, get them out. We're going to start doing some live coding sessions. You guys can all sit down, by the way. All right. So quickly, 3JS is just an abstraction layer on top of WebGL. Even though that it's synonymous with WebGL, it provides different rendering contexts. Canvas 3D, Canvas 2D is its fallback, the SVG renderer, and you have the CSS 3D renderer. So you can actually have CSS 3D transforms applied to DOM elements. Features, you have geometries that are built in for you, so you don't have to write all that crazy boilerplate code. You have materials on the top left. You have an object that's not interacting with light, which is called the mesh basic. The second one is using the Phong reflection model, which is the lighting within the fragment shader. On the right, it's the same exact lighting model, but it has ambient light. So you can see that the bottom corner is not so dark because there's a little bit of idea of global illumination. On the bottom, you can see texture mapping. Sorry, I promised you guys would be live coding. Give me just 2 minutes. We'll go through this really quickly. I would highly recommend, I'll share with these slide decks with you guys later, but here's an example of mapping. This is a very traditional example where you map a picture of a globe onto a sphere, but you can kind of see there, right? You can see that the water is more reflective than the land. And these are done via bump mapping and normal mapping, specular mapping. This is a very simple image mapped out over into a very simple sphere, which is actually quite smooth, but it gives the impression that that scene is actually a lot more complex than it really is. And again, this is what I was talking about, manipulating the normals of a given object. You can get this up in details. If you're interested in that, if this thing loaded quickly enough, I can show you how that works. Another useful thing, you'll be using this a lot, whether you want to get into 3D modeling yourself, or there are a lot of assets you can even buy online. But if you want to get 3D objects from Maya, Blender, 3ds Max, and whatnot into your scenes, you can do so. So you get the set of vertices, apply the mesh over those vertices, and apply lighting to them. Something I really want to do on my personal project, or my personal website. Who here is a car fan? I mean, I'm a big car fan, and the Pagani Zonda is my favorite car, right? So I want to get the Pagani Zonda model, put it in my website, and apply the different types of things that I want to do to it. Maybe drive it around on my website, for example. I can't afford the real thing, so. And the biggest thing that 3JS provides us is the object hierarchy. And this is huge, and it's very intuitive to work with. It's basically a scene graph. A scene graph is you can think about it as a very abstract tree. You have parents and you have children. And the reason that's useful in 3D transformations is that if you have a person, like, for example, like myself, I have an arm, I have a hand, fingers, and nails, right? If I want to move my arm, if I want to walk across this room, I don't want to go through every single one of these objects and apply transformations to them. That's quite difficult, to say the least. But instead, I create an object, being myself. I apply this object being an arm, and that object contains my hand, my nails. And when you apply a transformation at the top, the children's transformations are applied in a hierarchical fashion. So Scene 3JS provides that for us, and that's quite useful. Again, you can see here, you have a sphere. You mapped out this image, this very simple image onto the sphere. Then you actually take different types of manipulations of these images to provide bump mapping here. You have specular mapping, so the things that are completely white are more reflected than things that are black, as you can see here. And there are different techniques for achieving this. So I highly recommend you go through this example. It's quite cool and rewarding to actually build out yourself. And I think we're almost there, guys. So cool. We are almost there. And here is the famous example that pretty much all 3JS documentation starts with. It's drawing a cube. It looks like a square, but it's actually a cube. So you have a scene. You have a camera. We'll talk a little bit later about that. A cube geometry, 200, 200 by 200. This is not really, in 3D graphics, you don't think about these in pixels. There is no general consistent way of having these units kind of like mapped out to anything that you're familiar with. It's a lot more relative to your scene. You just kind of make out a consistent pattern. You follow along with it. However, 3JS, they kind of just recommend you to think within a standard international unit. But anyways, it's 200 by 200 by 200. You're applying the material mesh normal materials, which means that you're just basically mapping out the normals onto that mesh. You're creating a mesh, which basically is the encapsulation of the geometry of the material. And again, the scene is the root node of that scene graph, and you're adding that mesh on there directly. You create a canvas renderer. This is not the WebGL renderer. You append that child, which is the canvas element, onto the document. You call animate, which on request animation frame, it continually calls itself. And render, it renders a scene and a camera. And I guess if you want to know that this is actually a cube, let's see what this looks like. So mesh, good. Okay, so mesh.position.x equals, let's see if this works. Mesh.position.x equals, that's interesting, it's not even. Not sure why that's not working. I think it's the network not reloading it in time. Anyways. Let's make it a little bit faster and see if it works. It doesn't like it at all. Finally. Okay, cool. So I'm rotating based on over the x-axis. You can do the same thing over the y-axis. Let's slow this down a little bit. Oh, I thought JSPin was live. But anyways, we'll be building something a lot more complex than this. There you go. Cool. All right. Before we get started, one of my favorite quotes by Archimedes. He says, pretty much in short, the way I interpret this quote is, give me a starting place and I'll move the world. And as I mentioned, I love philosophy, so this generally talks about, give me a sound premise, right? Something that I can absolutely be sure that it's deductively valid. Give me that place and I'll move the world, meaning that starting position, as long as it's valid, I can deduce my way out. And I think that's very important. In 3JS, it provides us, obviously we're not talking about logic here, but it provides us a very sound foundation. And the fact that most examples use a cube, right, that's our starting point. So we're going to take upon the concept of a cube and build out our game 2048. So if you guys are all ready, let's get started. If you go to my GitHub, which is github.com/FarhadG 2048 cubed. Oh, the parrot? I love that bird. Yeah. Actually, it shouldn't be having the persona of a pirate on the open source world doesn't seem very. I should probably change that. So, all right, I'll give you guys a few minutes to kind of get situated here. All right, in the meantime, how about this? While that's installing, let's get started with the game itself, the overview, the parts of the code that we won't be writing, even though it's provided for you guys. Is everybody ready? Yeah? Cool. All right, at the root of this, by the way, I was hoping to have a secondary monitor here so I can code with you guys in real time, but even the second monitor is not working. So I just put the steps in for myself, so we'll be working with the steps in sequential order. That'll make a little bit more sense as we move along. So at the root of this, we have the index.js. By the way, just really quickly, this is just Webpack with a browser sync. So if you decide to bring React or Angular or anything like that into this project, it'd be quite simple. You have ESLinting, you have Mocha set up for testing as well. The version of the game should be tested as well. So if you want to write tests for this thing to make it a little more fully featured, that'd be great. I'd like to ask that this game, by the time we're done, this code base is nowhere out. So what I would love for you guys to do, by the end of this month, I'm going to create a little hackathon. So you have 2 weeks. You have my time if you need help. Contribute to this code base. Just put pull requests in. And whoever has the coolest example, I'll provide, whatever you guys are anywhere in the world, I'll send you some cool gear from WebGL. And I'll make sure you're a contributor to this game as well, because I'll be writing tutorial series on how to build this game from raw. So if you have any ideas on how to make this game better, contribute to it. I'll merge that pull request in and hopefully send you some gear as well. So anyways, writing tests is probably one huge thing, but didn't even get a chance to get to it. At the root of this, we have a manager. The manager is what basically controls the entire game. You have a controller. You can think about it. You can control it like a traditional, like an Xbox or a Super Nintendo controller. The controller in our instance is basically just a keyboard. It's very basic. The WebGL actuator is basically the WebGL rendering context. And the other example had an HTML actuator, which basically renders the entire thing to HTML and CSS itself. So this is the kind of a way I broke apart the code, is having these type of things only deal with what they're needing to deal with. So you can kind of swap controllers and swap actuators in and out pretty easily. Does that make sense? Cool. Guys, I want you to be loud, because if I say yes, does it make sense? The way the architecture of this code, because if you want to work with this code base, it has to make sense. All right, next up. So the manager, we'll cover that a little bit later. Controller really quickly. We're using a lot of ES6 features here. So I have a class constructor. I have a static set of properties. 38 is the up arrow key. 39 right, down, left, right, back, forward, forward. Basically, your question mark and your right caret key maps you out to forward and backwards. You have a set of events. On a given event, you basically set up the callbacks. This is just a traditional publish subscribe method. You emit and you listen. So on the listen is the most important one. On key down, you decide whether this thing is mapped up here, whether it's a key that we're actually looking for. If it is, prevent the default, emit, move with the map, whether it's up, down, right, or left. And what's listening to this is the manager. So the manager instantiates this controller and it looks for whether this controller ever emits the type move. You can have different things like rotation. If you want to rotate just the object instead of the scene, you can have many different types of things in here. So kind of give you an example. These are just movements, but you can do move, and then you can do rotate, and rotate could be, for example, your W, A, S, and D. Does that make sense? So you can provide a lot more functionality here, but this is just very simple code here. So let's get back to this. So that's the idea of a controller. A cube is basically, it's not a rendering of the cube. The rendering of all that stuff sits in the WebGL actuator. It's just the concept of what a cube is. You have, again, it's a class. It has a position x, y, z with a default value of 2. Most of these cubes are instantiated with the value 2 starting. Previous position. Later on, we'll cover exactly why the previous position is used for, and merge from. Previous position means that, hey, if you press right, did it come from that particular position, so you can do tweening of animations. And merge from, meaning that if you have two different cubes that are going to a particular position, I instantiate a new cube, and at merge from, I basically allow for those to transition onto that position, and I render a new cube. So if two twos collide, I render a new cube number 4. Does that make sense? So that's the idea of previous position and merge from. Save position is basically setting the previous position of the current position, and you'll see later on why that's useful. You update the position if you need to update the position of this particular cube. The grid is actually probably the most interesting part of this. You may think it's the WebGL actuator, but it's actually the grid. The grid, you pass on size, and I'm using, I believe this is ES60 construction here. So size is actually a 3-dimensional vector here. So what I'm actually doing, I'm deconstructing with an array. Width, height, and depth maps out to this, right? So I've set up map, height, depth. And then on the cells, I built empty, given the width, height, and depth. And what's really cool about this, right? So think about this grid. It's a 4 by 4 by 4, right? So quickly, how would you describe a cube like this? A 4 by 4 by 4 grid in JavaScript. How would you do it really quickly? Anybody? So you have imagine if you have a 2-dimensional array, it would be an array of arrays, right? So a 3-dimensional vector array will be X, Y, and Z, right? But what's really interesting about this is that if you have a 3-dimensional array, iterating over this 3-dimensional array gets quite expensive, right? So if I'm looking for a particular position, I would have to iterate over the X, then the Y, and then the Z. So this is to the factor of n3, right, n cubed. And in this game, how could I optimize this? One clever approach is that you represent 3-dimensional or 2-dimensional arrays as a single dimension. Now, do you guys have an idea how you would do that really quickly? It's quite simple. So here, let's just quickly do this. So here's 0, 0. And the cube example, let's just think about it in 2-dimensional space. 0, 0 is the top left. 1, 0 is the cube over to the next position. 2, 0, 3, 0. Then the next row would be 0, 1, 1, 1, 2, 1. Does that make sense? So this is the first position of the cube. 1, 0. 2, 0. Oh, crap. 2, 0. 3, 0. Then here you have 0, 1, and so forth, right? This is a 2-dimensional array, right? But again, iterating over a 2-dimensional array gets kind of expensive if you're constantly doing it per frame, right? So what you do, you would actually map this out into a single-dimensional array. So this actually would be like this: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? Because this is an array of length 16, which in a 4x4, it's 16 points, right? And the reason I decided to map a two-dimensional array onto a single dimension is because now you have linear time for iteration, for getting access, and setting data puts. And how would you do this? Well, it's quite simple, right? So you can think about the first 4 is your x. So you basically be a x modulus 4. Basically, this constant goes 0, 1, 2, 3, right? And then I want these 4, the next 4, to be actually mapped out to these, right? So it'll be, the y would be actually your y minus x modulus as well, right? And kind of see the code a little bit later in here as well. But anyways, this is a clever technique of mapping two-dimensional or three-dimensional arrays into a single dimension. And what's really cool is that conversion, it seems a little bit complex, but you get a lot of cool features from this. You don't have to do it. You can build it with two-dimensional or three-dimensional vectors. It's not necessary, but it's useful because as you can see here, I'm using Lodash. I'm ranging basically width, height, depth. I'm multiplying that, and I'm basically creating a single dimensional array, right? Range, what it does underneath the hood, range 4, it basically gives me an array of 0, 1, 2, 3, right? And I'm mapping over that, and I'm basically multiplying the range is actually width, height by depth, and I'm mapping over it and just getting default values of null. Does that make sense? So imagine this crazy three-dimensional array is described in a single dimension with one line of code, right? So the overhead is basically here, position to coordinates and coordinates to position. I feel free to look at this. It's actually not very complex math. You can constantly tinker with this code and understand it. So again, single dimensional, it's a lot of cool, powerful features here. Random available cell. I'm using another Lodash method called sample, which this basically does. 2, 3, 4. If I want to get random input, a random position that's available in this 3x3 matrix, or 4x4 matrix, or 4x4x4 matrix, since it's single dimensional, I just do dot sample over that array, and it gives me a random value here. Can you guys see the power of this so far? That in single lines, right, I'm getting data inputs, data positions from these grids. Make sense? But if it was a 4x4x4 matrix, I would basically iterate over this complex array-like structure to get one random data input, right? But since it's flat, I can do a simple sample over it. Available cells, again, super simple, right? Each cell, I go over it, I get the x, y, z position, and I return the cells. These are these things that I'm using. Position to coordinates, again, it's mapping a particular position in a single dimensional array to a 3 dimensions, and coordinates to positions the other way around. Another useful Lodash library or method or utility function, compact, occupied cells. So you have a crazy grid, and I want to find out all the objects that are within this grid. So again, 4x4x4 matrix, right, or 3-dimensional array here. I would have to iterate over all the x's, then the y's, and then the z's, and say, hey, if there is a value here, put it into an array and return those. Those are the occupied cells of a grid, right? But here, I'm using compact. And what compact does underneath the hood, 1, 2, 3, null, 4, it returns to me everything but null. And again, since it's single dimension, if there's a value there, that means that there's an object there. So there's just so many benefits of converting these multi-dimensional arrays into a single dimension if it's possible. Again, cells available, cell content. This is how you insert. So if you given an item with a 3-dimensional position, you provide that into the cells. Again, this is not part of the game. This is the game's logic. It has nothing to do with WebGL itself. But I just kind of want to provide this code for you that if you want to build the game and the grid structure behind it, this is how you would do it. And within bounds, again, the grid is basically 89 lines of code, and mostly it's a lot of helper functions to help you semantically work with the grid. The manager basically manages the controller and the actuator together. So as you can see, you instantiate the controller, you instantiate the actuator with the given size, the animations. Again, add random cube. It says, hey, add a random cube. Grid, cells available. Give me one, and then you insert that into the grid. Move. This is the more complex part of the app. It's basically determining when you press left, traversing the entire grid and finding what all positions that those cubes can move on to. Again, this is not part of WebGL. This is just the game logic itself. So definitely look at this code base. It's not. It's honestly like here it goes, 160 lines of code, and this is the beefiest part of this app outside of the WebGL renderer. So this is a quick insight about the app structure itself. If you guys are all ready, let's get into the WebGL actuator. I assume you guys have everything installed? Yep? Yeah? Cool. So if you've done npm install, you do npm start in a silent 2048 cubed, npm start s, and you'll run webpack and browser sync, and it'll be running on port local 8080. So open up the console on the bottom, immediately you see that there's an error. It says actuator is not a constructor because we have not built any actuators at all. So let's build this out. Export default class WebGL actuator, and let's see what we get now. So this actuator.actuate is not even a function because the manager, right, calls actuate on this renderer to render everything onto the scene. So let's just put that in here really quickly so the errors go away. Nope, not that. Actuate console log actuating. And later on we'll work with this. We'll build a constructor because it's a class. And there we go. We're ready to get started. Are you guys there with me so far? So we built a basic class with ES6. This is the same thing as, in case you're not familiar with it, function, WebGL, actuator. And then WebGL actuator office prototype dot actuate. This is equivalent, right? So, all right, cool. So if you guys can raise your hand, make sure we're here. You guys are all good? Yay? Nay? Some of you are coding along, some of you may not. Cool. If you have any problems, if you're coding along, just raise your hand if you have any issues. So first one, class. I was hoping to have this as a dual screen, but obviously it's not working, so let's put this here. We don't need a test file. Okay, cool. Can you guys see that? Okay, cool. So we're going to bring some helper functions, or helper libraries. One Lodash, and obviously we need Three.js. And those are all provided for you in the node modules. So we get past step 1. Step 2, and we're basically doing here, grid size and animations are provided by the manager, as I mentioned earlier. And in here, so inner width, inner height, and device pixel ratio, these are basically off of the window object. Grid size, again, I'm deconstructing width, height, and depth off the grid size that's passed in from the manager itself, top level. And I'm setting that to the constructor itself at this, so I can use it later on. Arbitrarily, I'm setting the cube size as being 5, and animation is the duration of the animation for one cube moving from one side of the screen to the other side, and what kind of easing curves that we'll be working with. So if you want, I can pause as you guys are typing this out. If you have any questions about some of these functions and what they mean, feel free to ask me in the meantime.
Do you have the solution of any branch?
I don't.
You're going to push it, right?
I will push that for sure later. See, I was hoping to actually live code this with you guys on the side, but the second screen is not working. So. Oh, are you? Okay. For those of you coding along, raise your hand if you're done, or if you actually it would be easier if you want me to wait. Wait, sure. So kind of give you an idea what the grid size and animations are about. Just put a debugger in here. So we have grid size. It's a 4x4x1, so it's just a two-dimensional. That's how the beginning of the app is itself. And animation, these are passed in again. The duration is 300, and easing, I'll show you what easing curve that I'm using later. So again, these are passed by them, by the manager, and we're just setting it to that instance. Should I raise your hand if you want me to continue waiting? We may fall kind of short on this presentation, so for those of you coding along, feel free to come find me afterward. We can do it together. All right, I'll kind of move past this because this code will continue to stay there. So the third one, this is actually finally drawing a cube onto the scene. As you can see, it's called 3Cube. We have a scene. And you know what? Let me just type this out with you guys here. So we do this.scene equals new t.scene. I'm just abbreviating T for 3 because I don't want to keep typing it over and over. Then you create a renderer, and we're going to use the WebGL renderer instead of the CSS or other renderers that they have. I got to make this a little bit smaller. I hope you guys can see this. So, is that fine, guys? All right, and on the right side, we're going to set anti-aliasing to true. This is just a way to render a little bit smoother images. However, it comes at a cost of performance, but I'll put that in anyways. The next up, you set the set pixel ratio. I'm obviously here in a Retina, so my device pixel ratio will be 2. What this is doing underneath the hood, you would actually draw the canvas element twice the size of my viewport, right? And then shrink that down to my given resolution here, right? And this kind of gives you the impression that it's much higher quality, always being Retina, right? But again, rendering this scene twice the size, it's a lot more expensive, right? So this is a nice way to kind of provide performance that you can do, and later I'll change this. You can do third of the quality, you can do a fourth of the quality, or you can go maximum quality, being device, the actual device pixel ratio, which on a Retina is 2. And I'll manipulate this later so you can see what that looks like. You set the renderer set size of the inner width and the inner height, which basically just tells the canvas to fill the entire screen. Then you append that canvas onto the document body via document.body append child off the renderer's DOM element. And here we create a camera, a perspective camera, which takes into account depth of an object. So as an object is further away, it actually gets skewed. So you can actually give the impression that there is depth involved. The first one is the field of view. It's the angle of your camera, how much you can actually see. The second, inner width divided by inner height, is the aspect ratio. This is generally inner width divided by inner height anyways, but you can provide custom aspect ratios. 1 is the near clipping plane. And the depth times cubic times at 40, you can put 1,000 here, you can put any number, but it's the volume of how much depth of your volume is being rendered onto the screen. So we can change this a little bit later, you can kind of see how that works. So we have a camera onto the scene. Then we do camera.position.z. In WebGL, actually in 3JS, it's a right-hand coordinate system. So if you kind of just grab your hand and point it like this, the right hand, if you point it at yourself, this finger points up, that means your y-axis points up, x points to the right, as you can imagine, z points towards you, right? So positive z is towards you. The left-hand coordinate system is, again, the same thing, but y points up, x points to the right, z positive points away from you, right? So again, that's an easy way to remember it. It's right-hand coordinate system, the z-axis points towards you. So we camera.position.z, so I have a cube here, and I'm bringing the camera position.z back, right? I create a cube, and we'll show you exactly what this generate cube function is doing. I'm going to add that cube to the scene. I'm going to call animate, and we'll walk through this code one by one really quickly. animate and generate cube. Let's see if this code works. This is not how I intended for this presentation to go, but we'll do what we can. Perfect, it actually did work. Awesome. So a very simple example of a cube onto a scene. Again, really quickly, we create a scene, we create a renderer, which is we need a WebGL renderer. We set the pixel ratio being this given format. If I bring this up, you could see that it's I'm not sure if you can see it from that screen, but it's perfectly smooth now, right? If I bring this down to 4, it's a lot blurrier. Can you see that? If you can't see it now, you can see it there, right? So that's the quality of the rendering. But let's go for maximum. So at Retina screen here. You set the size of the renderer being the full width of my screen, inner width by inner height. You append that onto the body because it needs a canvas element to actually render onto. You set the camera, and I'm pushing it back. As you can see, the cube is further away from the camera. Again, Z positive, it's towards us. Cube, generate cube. So let's go down here. I got the cube size, which I set as 5. Geometry, it's a basic geometry of 5 by 5 by 5. And mesh normal materials, basically material that is not affected by light. It's just mapping out the normals onto that material. And a mesh is an encapsulation of the geometry and the material. This is what's actually finally added onto the scene, because you interact with that mesh. You rotate the mesh. You don't rotate a geometry, because you want the material and the geometry to actually rotate together. So kind of to show you that this actually is a cube, again, we can do, how about this? This dot scene dot rotation dot x equals, and this is going to work a lot better for us. There you go. Cool. And if you notice what I'm doing here, I'm not rotating the actual cube. I'm rotating the entire scene, right? So the scene is actually rotating around me. Does that make sense? And I can show you, I mean, at this point, you really can't tell because we only have one cube. But if you had multiple cubes, you would see all of them moving because you're rotating the entire scene, right? And this is that whole thing I talked about, object hierarchy transformation, because I'm applying the transformation at the very root node, which is the scene, and all the children are actually being applied, right? So if you have many cubes here, they would be all rotating. But if I was rotating the cube, only that cube would actually be rotating. So we have that. Let's get rid of that. Next example, we have lights. By the way, guys, how's the pace? I know it's a little bit fast, but is it making sense so far? What's up? Sure. And don't worry, because I'm progressively building this. I'm literally taking you through the process of how I built this app. And I just like, hey, you build out a cube, right? Then you build multiple cubes and you put them on a grid, right? So we're actually going to be walking through this step by step. Oh yeah, so this is just kind of to show you that it was, so I'm actually applying, let's go over the y-axis. So you can kind of see that now I'm rotating over the y-axis, right? And in fact, let's just show you really quickly here. Let's get cube 2. Scene cube 2, cube 2 dot position dot x equals 10. Now you can see that the fact that I'm rotating an entire scene, both of them are rotating. Does that make sense? And by the way, did you see how easy that was? Because I created a function called generate cubes, right? It basically just applies that cube, gives it back to me, and I add it to the scene, right? Basically 2 lines of code. I created a new cube and added it to the scene. And if you wanted to see really quickly here, let's do something even more interesting. So just to kind of give you, actually it's not more interesting, but cube here. So instead of rotating the scene, let's rotate just the cube. And now I'm just rotating the cube. So if I added that second cube, that one would stay stationary. Believe me, take my word for it. Cool, let's get to the lights. I'm going to create another function here called add lights. And let's bring this here, add lights. Let's put it under generate cube. And by the way, how many of you have seen the syntax here? Animate equals. You've seen this, right? Can you raise your hand? Okay, what's really cool about this? The animate function here, right? This is traditionally, this is how it's supposed to be written, right? But if I wrote it this way, the this context changes, right? By using, I think it's ES7, I believe it's ES7 function bind, but by writing your function this way, yeah, and there are other methods for basically the double colon, which I'm not really fond of, but if you wrote your function this way, it's automatically bound. And you can use this in React, it's quite useful. So now I can actually do it this way, and your this continues to remain in the same context. And I usually put these functions a little bit higher so I can know exactly which ones I auto-bound. So let's get to the lights. And this dot add lights, and we're going to change the material because later actually. All right, cool. So let's continue to rotate that scene to kind of see what it looks like. Where's my animate function? This dot scene dot rotation dot x. Actually, you know what? Let's do dot. By the way, you can do setting it to x, y, z just like this as well. But you actually have to get the original. So rotation dot x, y at a different speed. All right, cool. So it's spinning, right? But however, again, this is the mesh normal material. It has no effect from lights. So let's actually provide the right material to this. So we're not going to use mesh normal material for that geometry. We're going to use, let's say, mesh Phong material. And we're going to provide it a color of red. So now this is actually affected by light. And can anybody guess why one side is so dark? And only one side is lit up like that. Okay, I'm sorry, what was that? I'm not moving the light yet. Oh, good. So, yeah, I'm sorry. Actually, can you say that a little louder? Because it's a great point. Absolutely, right? And when I first saw it, I'm like, what the hell is going on? Because you only have one object, and I thought I was rotating just the object, right? So if you have an object and you have a light source and you're constantly rotating it like this, you would think that it's going to constantly light up. But we're not just rotating the object, we're rotating the entire scene. And the light is part of that scene. Again, that hierarchical object transformation, you're rotating the object and the light together. And I'll show you later exactly to see that. Nice catch, by the way. But kind of get a little bit of the fact that this is not very natural, right? An object wouldn't be completely dark on one side, even though if there's illumination from one side, right? With a simple ambient light, this is just a simple global illumination. I'm adding the color white here. You could see that you have a little bit there, a little bit more, but let's just bring this down a little bit. And it, by the way, accepts hex values. There you go, right? Then again, I'm still moving the light with the scene. And if you want to see that, let's go to the next step. Let me just figure out if I can do it really quickly. Constant point light helper, new t point light helper, if I can type. And we're going to take the point light as its first argument, and I'm going to provide it just a size of 4. Scene.add point light helper. Can you see the light source? Let me just slow this down a little bit quickly. Where's my render? So let's go 0 and 0. All right, see, I'm rotating the scene, and there's a light. Do you see that? So that's, by the way, nice catch again. When I first saw it, I'm like, what the hell is going on, right? So again, a lot of times when you're working with this stuff, you're like trying to figure out where objects, how their orientations are. So it might be a little bit confusing. So you have a lot of useful methods like this, like geometry helpers, light helpers to kind of help you. A point light is a light that emits light in all directions. You have directional lights. So if you had a directional light helper, you can actually see the cone and which way it's actually oriented. So we have lights in the scene. Next up, we have a cube container. And what the cube container does, let's get to that really quickly. And I'll show you exactly what that is. All right, so I added a function here called generate cube container, and what that is, so again, I was mentioning that you have some sort of node and you want to apply many different children to it, right? And in 3JS, you have this thing called Object 3D. It's just a theoretical containment of 3D objects. So I create this one, and I create a generate cube container, and I'll show you what that is. I apply that cube container, which is the collection of all my cubes. So instead of attaching all the cubes to the scene, I make one object 3D, which is my entire cube. That's how I'm able to rotate the collection of all cubes, and I attach the cubes to that cube container. Does that make sense? This is the way that when I was rotating the entire scene, the scene was not rotating, just a collection of cubes were. So this is just me creating a node and applying all these different cubes that you'll see later on in the scene to that cube container, right? So you can think about this that you have a div, and that div has many elements within it, or you have an unordered list collecting a collection of many list elements. So let's see what that looks like. Here it is, right? And you can see the light source is still there. So cube container, object 3D, I generated the cube container, and this is very similar to generating cube. However, I'm just using the Lambert material because it's not very important for me to have Phong reflection models. And if you look at the documentation, the difference between Lambertian and Phong. I'm setting the color white, transparent, it's true because I set opacity and I put it in wireframe mode, which allows for you to do that. If I didn't take that, you could see that it's basically like this, right? So I put it in wireframe mode. So you can kind of see that. And this is the basis of my 4x4 grid, right? Making sense so far? Great. And I'm going to start rotating the scene because I think it's getting a little disorienting. Where's my animate function? Let's get rid of this. Cool. Now, the fun part. So what do we do here? I'm not going to call this function just yet. I'll put it up here. All right. So now, I created a cube just like before, right? And I pass in the color blue for my generate cube function. I get XYZ from this coordinate position converter, and I'll show you exactly. It's very simple. I set the position of that cube, like as we did before, position.x equals this, but I'm just setting XYZ at the same time, and I'm deconstructing this. And I basically, again, this.scene.add cube. Technically, this should be this.cubecontainer.add cube, right? Because as I mentioned, we'll be adding the cubes onto the cube container itself, right? And how did I get it to be the top left, right? So again, 0, 0, 0. How about this? Let's kind of show you how this works. 0, 0, 0. Again, in geo-coordinate space, 0, 0, 0 is dead on center, right? So what I want is for 0, 0, 0 to be here, 1, 0 being here, 2, 0 here, 3, 0, and then it kind of ties in really well with the grid that we had of mapping a two-dimensional or three-dimensional array mapped onto a single dimension. However, I still want 0, 0 to be here, right? So what do? I create a very simple helper function for converting these positions. So given x, y, z, I get the cube size, which is 5, as we mentioned earlier. We set that. Half cube size, and you'll show you later how that works. You basically set the position of x. So if it's 0 times the cube size, so if it's 0, 5, second is 10, 15. And the reason that I need to minus based off of this is because 0, 0, instead of it starting from dead on center, I'm translating it half of the cube container's width. And I do the same thing for the height. And to kind of show you how this works really quickly, so check this out. If I added, change this to 1, you can see that it got pushed over a little bit, right? Let's push this to 6. Right, how come it's not working here? This dot coordinates position, x dot cube size. Oh, times width. Am I not applying it to the right position? This, that. Where is the, oh, of course. Again, this is the whole thing that I was talking about, that cube.position.set x, y, z. Right? It's all the way up here, right? So 0, actually I don't need to apply width to this anymore. So, right, 0, 0 is mapped over here. If I push it up to 1, slightly 1 over, based off of its width. So that's why I'm applying this little offset here to have the translation start at the beginning. Our cube.position.set x, y, z. Bless you. So if I push it to 1, you can see that now, right? 1, 1. Does that make sense? Right? So I've mapped out that center coordinate space onto top left of my cube container. And again, this is not something I just right off the bat knew. You just experiment with it. You keep tinkering with it until you get the right positions, and then all of a sudden it clicks, right? So then I have this helper function that helps me convert from x, y, z being dead on center to this cube container being top left. Let's get on to the next position. This one's called many cubes. Sorry guys for the multiple windows, my screen is quite small here. So many cubes. Again, I'm a big fan of Lodash. Again, I'm ranging, I'm getting 4 inputs, and I'm mapping over them, and I'm getting z, y, x first. And the reason I start with z, because the inner function x, I'm incrementing x first, and once x is done, I increment y, right? So just kind of give you an idea of what x, y, and z looks like. You can see it right here below it, 0, 0, 0, 1, 0, 0, right? 2, 0, 0, I'm incrementing the x values, then the y values, and the z values, right? You can go the other way, it works perfectly fine. But now, I mapped out over every single combination of this, and I completely filled out my cube container. Making sense so far? What's that? Sure. The cube container? Here you are. Yeah, it's wireframe, exactly. Yeah, exactly, man. Are you coding along with this as well? Nice, man. Cool. So does that make sense? How so useful, right? This is like literally what I did. I created a cube, I created this cube container. I'm like, all right, I want to see me in top left. I got that, then I rendered the entire 4x4 matrix. And it literally, in a few lines of code, ranging over this, I get all the x, y, z possible coordinate spaces, and I add that to the scene. Yay? Good? Cool. Next one, environment mapping. So how does this work? So let's go back to our example here. We created a scene. So this is actually quite clever. We have negative x, JPEGs, positive y, positive z, and negative z. Creating a cube texture loader. And this is how you mimic an object being in a 3D environment with infinite distance. And what you're actually doing, you're creating the entire scene is sitting within a cube, right? And I'm creating images and I'm putting it on the sides of the cube as if you're inside of this world. And it seems like, no way, how does a cube with these sharp edges feel like you're actually part of this immersive experience? And how that works, I provided the assets for you guys already. Here's the clouds that I used. For those of you familiar with Photoshop, it's quite simple. Here's the image, right? This portion is the top, right? This is the bottom, negative y. This is forward, which would be, again, negative z, right? Because positive z points towards us. This side is left x, which is negative x, right x, and this is the back. So it would be, I'm sorry, this is actually negative z, and this is positive z, because this is pointing behind us. But you can kind of imagine I'm mapping these images onto a cube, right? So I've mapped these out already for you, right? And the reason why this is really cool, as you can see in this image, this part of the image maps out exactly to this part of the image. So once they're actually wrapped around a cube, and once you're inside of it, right, it looks like you're inside of this immersive experience. And it may seem crazy, but since this particular material is not affected by light, you don't actually even see the seams of a cube. And this is called cube textures. You can also do spherical environmental mapping. That's a different algorithm, so you can be inside of a sphere. This works really well with videos. So you can be inside of a sphere and map an entire video around it, and you can kind of look around. That's how you do a lot of these immersive video experiences. So in a few lines of code, check that out. We're in a scene. You don't believe it yet because there are no controls. We'll add that in. So let's go to here. Unless I missed that. Excuse me, guys. 1 second. Here we go. I did miss it. So to kind of give you an understanding that we are actually sitting in a 3D scene, a little nice helper function is called the 3JS orbital controls. This allows for you to actually rotate the entire scene. I'm passing the camera onto it and the canvas element, and enabling keys, which allows for you to use the keys to rotate, but I'm not going to be using the mouse. Damping allows for you that once you let go of the scroll, there's some sort of damping effect, that it doesn't stop immediately. There's some sort of damping there. And enabling zoom, I am able to true. So what that means now, so I have the scene. If this works, let's see, what am I missing here? I'm probably missing the import. Yeah, there we go. So let's bring that in. I just need this. You require it in, and you pass 3JS as its argument. It's a higher order function, it appears like. And WebGL, let's see, what does it need? This.render. Is the renderer applied later? This.render.out element. Where do we add this? Line 55. WebGL actually, or line 23, I'm sorry. So this dot controls, this dot, that's interesting, hold on. Any orbital controls, this dot camera, we have access to it, there we go. It just wasn't initialized at that time. Cool, so this allows for you to rotate the scene now, right? And we are actually sitting inside of a cube, right? And you can't even see the seams here. Pretty cool, right? So this is a simple way, instead of rendering complex scenes, you would basically render a large cube and map out these images over that image. This is the idea of texture mapping. So next up, cube textures. Let's bring this in. And what's the other part that we need to type out? Let's bring this to here. We need to pass in sample. And we'll get to this really quickly. Okay. And the materials for, we have to change that because we're actually mapping out textures onto that cube. Let me just minimize this so it doesn't seem. Generate cube, font. Okay, cool. I'm having some sort of syntax error, so let's go back. This looks fine. Let's go back here. I think I messed something up royally. So we have this. We generate cube. We need this over the reflection model. And we already have this, I believe. Generate cube over that. And our cube visuals. So let's bring that here. All right. So what this is doing, if it loaded, color is not defined. Oh, it's down here. Generate cube. So we have texture, color, and cannot read texture of undefined. This is line 109. So generate cube. Let's see what's calling this. sample.queueVisuals, and I know why, this dot load queueVisuals, cannot read texture of undefined. Let's see here really quickly. It seems like these images are not, it's undefined. Okay, great. So this dot load queueVisuals, oh, I got it. Okay, it's just returning it, so this dot queueVisuals equals this dot load queueVisuals. Perfect. All right. So what this is actually doing, before we were generating cube, but we're now, instead of just having a random color which we applied as blue, we're getting just a sample, a random texture from this little helper function that I wrote. So 2 is that value being color red, 4 being cyan, 8 orange, and up to 2048. Again, this game could go on infinitely. I wouldn't recommend creating textures for each one of these images, and I can kind of show you what that looks like really quickly. In the assets, you would see that I created these assets for you, right? These are textures that I've applied over each one of those cubes. I would recommend that since these numbers can go infinitely, you can create bitmaps. So you can have the 2, the 3, the 4, and actually combine them together, having composite textures. So I'm also then iterating over each of these values, and I'm applying the texture, right? So not just the color, but as well as the texture inside of this. So then up here, when I do this dot load cube visuals, and I have the cube visuals here, I generate cube, and I create grab a random one from these cube visuals. So then later down here, in a generate cube, I have texture and color. So I map it onto that texture. I apply the color. I apply the scene background, which is the clouds that we showed earlier, as an environment map. I add shininess as 20. You can mess around with this and get the desired output that you're looking for. Transparency later on we'll use because as I opacitate the cubes as they come in. Reflectivity, 1 being the maximum, 0.7, it's 70% reflective. You can think about it that way, I guess. So you can see here now, I'm rotating the scene, and the light source is up there. I kind of, later on, we'll put the light source where the sun is, but kind of give you an idea. Reflectivity, let's go to 1. So you can see that these things are a lot more reflective now. I'm not sure if you guys can see it. You can see the white cube, right? And if you want shininess, let's go to 100. Can you see that? Right? Cool. Anyways, feel free to kind of mess around with this. The color palette is not the greatest, so, but it gets the job done. I'm sorry? Oh, absolutely. So yeah, underneath the hood, the texture mapping is all done in the shaders, right? But what's just cool is that texture mapping is already done for you. It's so much simpler, right? So you don't have to map these coordinates yourself. Yeah, great question. The colors, for example, when you apply that color, that's done in the fragment shader, and the lighting, right? All the lighting calculations, the specularity, this is the Phong reflection model. Let me see, I took off a lot of the shininess already. But yeah, absolutely, this is already done for you in the shader. I'm sorry, if you can... No, that's immediate mode as well. Yeah, absolutely. So let's go here to the next level. So we have cube textures, like an actuator. Cool. So this is the part of the app that we're finally getting onto. The actuate function is actually the one that we wrote earlier to get the app working. And what this essentially does is that it gives you a collection of cubes that need to be rendered onto the screen. So I'm saying on the next request animation frame, clear the entire container. And clear container, basically, again, the cube container, again, was that object 3D that we attach all the different cubes to. We clear all of its children. And the reason for that is that to keep this game a lot simpler, every single time that you press left or right, the actuate function is called, you clear the entire container, then you render all the cubes, and if the cube has a previous position, then you rotate it to its final position from its previous position. Does that make sense? So because WebGL is really fast at rendering this type of stuff, you clear that entire container, you set the new cubes onto the scene, and you tween them if they need to be. So this is what's happening underneath the hood. Actuate is called by the manager. You clear the container and cubes for each cube. You add the cube. And again, I'm using the ES7 function bind here. So you can see here console log cube. You can have all of these cubes if they were in a scene. You have 3 cubes, but obviously we're not rendering the right cubes. We already filled the entire scene with other cubes. But you can see here that the manager, the top level, is providing this data for us to render. So tweening. Let's get this to add cube and make it a little more interesting. So tweening, as you're familiar with it, it's kind of like, maybe you can think about like CSS 3 animations, is the ability to translate or animate one object from one position to another position. It could be opacity or other things like that. And tweening in this example is just as a nice utility function for helping you interpolate between different values. So you have a position. Again, we're using x, y, z being 0. We're converting that to our coordinate position that we asked for earlier. We are setting that position. It's called a generated cube because we're no longer going to be using these cubes anymore, because this is just for us to kind of understand what was going on. You translate tween, so here it is. Cool. You create a new tween, and this is a library, again, that's provided for you within the boilerplate code. The position, which is the current position, being at 0, 0, 0, top left, right? To the new current position being 3, 3, 0. It's in the bottom left forward, not in the back of the cube, right? So we're tweening from this starting position to this final position. And on every update, so at every single tick that this is tweening is being updated, we're getting the x, y, z values here that we're tweening, and we're setting the cube's position to x, y, z. Does that make sense? Very simple, right? One starting position, final position, and every single time that it gets updated, we're updating the position of the cube. Easing, I'll show you a little bit later how that works, but in order for this to work, we would have to get, I believe, is tween dot update, and the reason for that is because we want that tween to be updated per every single request animation frame. I think this should work. Let's see here. Oh, we got to bring the library here. Import tween from, oh my God, what happened here? Import tween JS. Okay, cool. So line 129, we have an error here. Let's see what's going on here. This.cube visuals.value. Let's go to 2. Let's give it a random value here for now. Great. So you can see that I'm positioning from 0, 0. Actually, let's just make this 0, 0. We're not even tweening it. Top left, right? Nothing is happening. But let's go to X1. Loads, go to the second spot, right? And it's a linear interpolation. If I want to add different types of easings, the one that I found nice for this project was the elastic in-out. And I mean, that's actually not for this project. That's actually the hideous one. I want to show you how it kind of bounces. The one that I use, I think, is the cubic one. But let's go to X3. You can kind of see this effect more. You kind of see that it bounces, right? You can make this time for 1 second. Can you see that? Really simple, right? A few lines of code, you can get the effects that you want. And you can imagine that if you want to have different types of tweening when these two objects collide, you can have some kind of bounce happen here. But I try to kind of mimic the original functionality of 2048, that they kind of collide, one scales and kind of comes back in. So that's tweening. And here's the biggest part of this WebGL render, which is called the actual add cube. And we'll talk through this. So the cube, as is passed in by the manager up top, we get duration and easing, as we saw up top in the constructor. We set these up. The cube here has an XYZ value being 2, 4, 8, 16. Previous position, as I mentioned, if that cube had a previous position, we use it for tweening, right? If it didn't have a previous position, we just render it exactly where it needs to be. Was merged. This is useful for determining whether when the object gets to a final position, if it was merged, I take it off the screen, right? And merged from means that you have a cube, It's new. It just came into the scene, but it was a merging of two different cubes. So a cube 4 comes into the scene, and it's a collection of two different cubes being 2 and 2. And I use that so I can render onto the screen of having two different cubes collide to one another. Position, again, you're converting that position to what you need off the previous position. You say if it's merged from, you actually iterate over each one of those things that it merged from. You render those onto the scene. Again, it's a bit recursive here. This.addCube. So you just render all those previous cubes that they were merged from. You're saying if there was a previous position, you get the previous position and you tween to its final position. And on update, you basically update the position of that cube. And on complete says that once the cubes collide, take the 2 out of the scene and bring the new one in. Appear. So again, I just took the tween concept and just took it a little bit step further. Scaling and opacitating, if that's a word, of that cube. So as a new cube comes in, it scales to 1.2 and then it goes back down, right? And it also opacitates from 0, 0, as you can see from the bottom here, to 0.6 to finally 1. And the reason I did it this way is because it starts on appear start tween, then I chain it to appear end tween. So once this one is done, I chain it to this one as well. And at the end, you get this. So I hope you can see with some simple, I mean, obviously, like in this demo was quite quick. I was hoping to actually code this with you guys alongside, but I think if you decide to build this out again, you can follow the similar approach that I did, is building a cube, positioning it within a grid, building out multiple cubes, adding lights, and just slowly making it a little bit more advanced. And let's again go back to our index example. Let's add an extra dimension in here. And since the grid is already taking care of that for you, it's already there for you. And if you want to make this, for example, 2 by 2, you have that. Anyways, I know obviously that the demo we're about 30 minutes over. Question for you guys. What kind of other features would you put on here on this game? So some things that I had in mind, for example, is having, so we're using basic textures and colors, but you can imagine 2048 is the final goal, right? You can create complex shaders like a fire shader or something like that, that once 2048 gets captured, that cube turns into a fire, for example, right? Or fireball, right? You can apply physics. You can bring in a physics library to have simulations. So maybe when you win the game or the game is starting, something can hit the collection of cubes and they kind of just disperse out throughout the scene. There's a lot of cool things you can do. The code base, I'll be publishing this very soon. If you have any questions, come find me today and tomorrow. I'll walk you through the code step by step. But I would love, by the end of this month, it's a challenge for you guys. Take this code base, build upon it. If you have any ideas, I'll help you build it if you can't. Any questions you have, feel free to just come find me. Again, whoever has the best example, if you're interested, you're curious to continue building upon this, I promise you I'll send you something really cool. So, any questions? Yeah. Yeah, I mean, 3GS has been around for 5+ years. It's a great question, but I understand it as being purely built on WebGL standards. However, Ricardo, all right, guys, I'll share with you something that's really useful for me. Feel free to use this. Let's go to 3JS. By the way, a lot of cool examples. The documentation is kind of thin, but there's a lot of examples that you could use here. But let's go to 3JS GitHub. This is something that I do. I'll share with you a little secret that I love in open source development. I have this little bookmarklet that I built. Feel free to use it. It's on my GitHub. So there are 15,000 commits. I actually go to first commits of all repositories, and I follow the code base. I think it's the greatest way to learn code, if this works. So this takes you to the first commit, and you can see in 2010 was the first commit of this. And I actually followed this code base. I wanted to understand how Ricardo was building this out and where he fell down, where he kind of built upon it. And you can see originally he actually started out with I believe it was actually like just a normal canvas 2D renderer, because WebGL at that time was not even a standard. So anyways, whether it's for this project or any other projects, it's a really cool way, because I think open source development is just not one particular individual building something. you can just literally go back to the first commit and just follow the code base through. And 3JS, if you can understand that code base from ground up, you're a pretty badass graphics programmer. So, but yeah. Any other questions?
What real-time projects have you used WebGL for?
Yeah, that's a good question. So previously, as I mentioned, I was working for an open source company, building a 3D rendering engine. So one of our primary focuses was how do we build a lot of web applications using WebGL, right? So let's go here really quickly. If you go to YouTube, I think this is a cool example. We built out, like I was actually telling David Kerr here, famous, let's see here. That's not the one I was looking for. Because, I mean, a lot of times when people, they experience WebGL, they're like, why is this thing, why should I be even using this thing? Some other websites that I've been inspired by, I think you should check them out. But so here is a very advanced carousel or cover flow. This was actually used by a particular company that wanted for us to build something out for them. We actually helped build, like, Flipboard. We built like a canvas renderer version of, like, a kind of experimental version of their app using WebGL. But you can see here that you have a traditional carousel, right? And again, this is DOM and WebGL living in the same coordinate space. But you apply 3D transformations. And this is kind of like a nicer way to kind of go through a gallery. Imagine for, like, you're walking through a museum. Generally in a museum, the reason the artwork is so important because you're walking to the artwork, right? It gives the impression that the artwork is a lot more important than you. That's why you're navigating to it. And having that type of experience in the web is pretty cool. So now you have lighting here, for example. You apply the fact that they're turned kind of into glass shards. So yeah, we build a lot of examples like this, like taking common interfaces on the web. And that's kind of the reason I thought of in 2048, taking something that's already on the web and applying 3D principles to it. But obviously, in not all situations it's useful. But I think for something like a carousel, it's useful. So yeah, it's actually turned on all modern browsers. Yeah, I mean, as long as the GPU, which is quite powerful, it's good enough. Some libraries that are out there, they have React and 3JS integration, so you can actually use WebGL components within 3JS. Check that out. I've been working on a Babylon JS/React integration. So yeah, feel free to use it in a lot of these mobile and desktop applications. Right. Any other questions? All right, guys, thank you so much for your time. Sorry for taking up too much of your time. My apologies.